Hello everyone and welcome to this webinar session. My name is Mélanie Gaillet and I'm the moderator today. I would like to introduce you Romain Bruder.
Good afternoon.
Our fluorescence product specialist in HORIBA Scientific, as well as Renald Orto.
Hey everyone,
Renald,
thank you.
our application expert. Today we will talk about the latest innovation in fluorescence spectroscopy developed by HORIBA Scientific, and especially the use of CCD and array detectors in new systems or new configurations. We want to show you how to expand to the third dimension your data for a maximum amount of information about your samples. Let's now introduce the outline of this webinar. Romain will start with a short introduction on spectrofluorometry and general concept. Then he will focus on CCD detection and he will explain you how it is a real breakthrough for fluorescence. Then we will go in the lab with Renald and he will present you our new system, the dual FL, which uses CCD detection. Then we will go back to Romain for application examples that will be illustrated by a live demo of the dual FL. Few words to conclude about our expertise. The timing of the presentation is about 30 minutes. Stay with us and do not hesitate to type your questions at any time during the presentation in the Q&A box. So enjoy this webinar and let's start right now.
Nowadays, fluorescence is a well-known technique in the toolbox of modern researchers. Based on the interaction of light with the matter, it presents various advantages in terms of sensitivity, selectivity, ease of use, and limited sample preparation. But fluorescence is not really a recent phenomenon. The first reported observation, besides naturally occurring phenomena, has been reported in the 16th century by Spanish and Italian scientists. They described the phenomenon of light emission of a wood infusion known as lignum nephriticum, for which the emitting compound was multiline. Multiline is the oxidation product of one of the flavonoids found in this wood and emits bluish and greenish light under natural light exposure. But it was necessary to wait until the beginning of 20th century to better understand and describe the phenomena based on major discoveries made in the field of quantum mechanics and chemistry. The picture on the left represents a Jablonski diagram. It figures the different electronic states of a fluorescent compound and the excitation and de-excitation path when exposed to external light source. From a dynamic point of view, here is what happens. The light received by the fluorescent material is absorbed within femtoseconds through an absorption process, making the sample reaching an excited electronic state, in blue on the picture. A part of the absorbed energy is lost through internal conversion or heat exchange to the environment, for the sample to go down to a lower excited electronic state. The final step of the process is to get back to the ground, non-excited state, which is the most probable state for a molecule in absence of external source of excitation, in green on the picture. This last step is accomplished by releasing the excess of energy under the form of light, making the phenomenon of fluorescence. The wavelength of the photon which is released corresponds to the gap between the ground state and the first excited state, making the phenomenon specific to a kind of molecule or bonding. The competition phenomenon, in red on the picture, allowed for some molecule due to the structure, involves a specific level, the triplet state, which has a long lifetime. This is known as phosphorescence. Fluorescence is now a mature technique used in a variety of fields. These fields are nearly unlimited, from biotechnologies to nanomaterials, from semiconductors to more general material science, but also in environment or food analysis. Within these fields, numerous examples of application can be found. For instance, to unravel the complexities of the microenvironment of molecules, to study molecular mechanism of transmembrane proton transfer, to use fluorescence for photodynamic therapy studies to locate some tumors, but also the study of biological process like photosynthesis, the characterization of photoreceptors like flavins and carotenoids, drugs analysis, hormones, proteins, DNA in the biotechnology field, to create and generate investigations by fiber optics invasive system in medical and clinical manufacturers, or in the field of cosmetics and healthcare to study, for instance, sunscreen or skin quality. From the instrumentation viewpoint, the most common device that is available for spectrofluorometry is the scanning spectrofluorometer. It features different components. First, a source which provides the excitation in a large spectral range from UV to infrared. Then, an excitation spectrometer which allows to select the wavelengths of excitation and to send monochromatic light onto the sample. The sample compartment, where a variety of type of sample can be placed, from solid, liquids, powders, thin films. A second spectrometer for the fluorescence analysis, which scans the light which is emitted by the sample. Then a detector to record the signal, and of course a computer to control the wavelength scanning and the data collection. Yet a mature tool, there is still open space for innovation in the fluorescence field. Here are some examples of newly developed instruments in HORIBA Scientific. First, you can find some Delta Pro TCSPC system which study lifetime of fluorescence based on very simple filter spectrometer. We also recently released a Delta Mic lifetime microscope, again to study lifetime of the fluorescence at the microscopic level for different type of application in bio and material science. But also we have the well-known Fluorog 3 from HORIBA Scientific, which can now be equipped with array detectors for some particular configurations, such as an analog for carbon nanotube analysis, for instance. So today, new trends arise. Fluorescence is not only a research topic, but becomes more and more a routine tool for various application fields. The instrumentation requirements evolve as well. The instrumentation needs to comply with all the quality control requirements: fast analysis, little sample preparation, simplified workflow and interface, easy interpretation of the results. The samples are no real and no more ideal sample. They present very high or very low concentration, which induce that the system must be able to fight against sensitivity or against saturation of the detectors. You need to be able to correct from inner filter effects linked to the sample. You need to be able to filter interference of other compounds. And in this respect, array detectors and CCD are the tool of choice. CCD is a real breakthrough for fluorescence. It's a two-dimension detector which enables to collect the light across the full spectral range simultaneously, rather than the scanning monochromator, where you scan a monochannel detector by moving the diffraction grating. CCD offers fast analysis. Then you collect this full spectrum in one detector exposure. This opened the way to easily acquire excitation emission matrices, EEMs, to characterize fully the sample. The sensitivity of the CCD enables also to have a good dynamic and to avoid saturation. We'll see just after what it means. CCD also feature a good linearity of the signal and offers the possibility to have easy and automated data treatment. How does the CCD work? In order to produce an image or a spectrum, a CCD must accomplish four functions. First, generating photoelectrons, then collecting electrons, then again transferring the collected charges, and finally read the charges. The first function is based on the photoelectric effect. The light absorption in the silicate network of the CCD generates these photoelectrons in proportion to the number of incident photons. The latter are immediately collected in pixels, closest to where the photons fell on the chip. Those pixels are defined by means of an electrode network which covers the surface of a CCD. The electrodes form potential wells to prevent the collected charge from escaping. When the collection of the charge is finished, the transfer is realized by changing the potential of each electrode in a synchronized way. Therefore, electrons can move from pixel to pixel and finally to the counting device at the end of each line or column. The output register consists of a series of electrodes which lie outside the photosensitive zone of the CCD and perpendicular to it. Then, this output register sends each charge package to an output amplifier, where charges are digitalized and stored into a computer hard disk. Afterwards, the register signal can be calibrated, analyzed, and treated afterwards. CCD has also a great advantage. It is highly efficient in terms of quantum efficiency. In the figure above, the quantum efficiency of different types of CCDs as a function of wavelengths are compared. You can notice that the eye has a quantum efficiency of around 1%. Therefore, we can only detect one single photon in hundreds of photons that hit our eye. In contrast, more than 50% and more than 80% at certain wavelengths of photons falling on the surface of the CCD are detected. Additionally, the spectral range of an eye, for instance, is way narrower compared to CCD. This limitation is also affecting other detectors like PMTs, photographic plates, and so on. But if a CCD is illuminated from above, it is rather insensitive to ultraviolet light, since the electrodes surrounding each individual pixel are opaque to these photons in ultraviolet. We can improve the quantum efficiency in CCDs in the ultraviolet range by about 20% by coating the upper surface with a thin layer of phosphor, which converts ultraviolet photons to photons with a longer wavelength. But an even more efficient method is to illuminate the CCD from the back, so-called back illuminated. Therefore, the CCD itself has to be thinned, and the incident photon can then enter into the photosensitive area of the CCD without being absorbed by electrodes. This technology is used in the CCD we are using in our new systems. CCD also presents a good linearity of the signal, meaning that the correlation between the number of incident photons and the signal which is read is good. The figures on the left show the linearity of a PMT. As all the photons are collected onto a single sensitive surface, it can be prone to saturation, then losing the direct correlation and linearity between the number of photons hitting the detector and the signal. For the CCD, on the right, the saturation can occur at the pixel level, but if the photons hit different pixels, those pixels can be summed together to increase the overall collected signal. This enables to keep a good linearity without saturation over a large dynamic range, thus enabling to analyze some very concentrated samples. Spectrophotometer with CCD and array detectors are now more and more common in our portfolio. You can see on the top of these pictures the dual FL. You will be given a demonstration just after. This is the world's fastest fluorimeter. But CCD and array detectors, they are now available and some other products in our portfolio, such as the well-known Fluorlog 3, which features a true double monochromator and gives flexibility and ultimate sensitivity. In some configurations, such as the nanolog, it is dedicated, for instance, to analyze carbon nanotubes. CCDs are also implemented on a dedicated version for water analysis of the dual FL, the Aqualog, which targeting fast excitation emission matrices and data treatment for water analysis. To illustrate the two-dimensional detector's benefits, I present here a comparison with classical PMT detectors. This is an example of what can be obtained within seconds with a CCD. When the spectrofluorometer is scanning, the PMT acquires a one-dimensional spectra, intensity versus wavelengths. Meanwhile, a CCD can record the full spectrum for each position of the grating at once exposure. Then, when scanning, the CCD records two-dimensional maps, which are intensity versus excitation wavelengths and versus emission wavelengths. Here is another example of what is possible to do with two-dimensional detector. You see here on the left an IM, Excitation Emission Matrix, obtained on some single-wall carbon nanotube in the infrared area. This IM enables to have a view of what is the fluorescence behavior of the sample in excitation and emission, and you can detect some very different patterns. Thanks to specific software routines, the nanosizer, here in this case for carbon nanotube, you are able to extract helical maps of the distribution of what you have in your carbon nanotube sample. More generally speaking, fluorescence reveals different size of the carbon nanotubes and different helical distributions which are dependent on the sample preparation method. Now, let's join Renaud to the lab for a guided tour of our new dual FL system.
So thank you, Romain. Let's try to illustrate what you just said with this new instrument from HORIBA Scientific, the dual FL. So same family as the Aqualog. That type of instruments, benchtop instruments, is based on CCD, as we mentioned. So these instruments can be divided in three main parts: an excitation arm, a sample compartment, and an emission arm. Emission where we are going to record the different signal that we can get. So first of all, the excitation part. So this excitation part will be based on a setup, simple setup that has been designed by us, of course, where we can get a high intensity, broadband, low noise, tunable light source. This light source, this beam, will come inside the instrument. So before entering inside the sample compartment, we will get a reference diode that gives us all the information concerning the absorbance before the sample itself. Then we have a really smart design sample compartment. This design will allow us to measure simultaneously, and this is really a great advantage for this instrument. So to measure simultaneously the absorbance and the fluorescence signal from the sample. So in the line, you will see we will get the absorbance signal. So as I mentioned earlier, there is a reference diode before this, so we will be able to compare the two signals. Again, the absorbance will be measured, and at 90 degrees, we will get the fluorescence signal itself. So the fluorescence signal will go inside the instrument, inside a spectrograph. The spectrograph attached to a CCD, which allow a large, relatively large emission record for the fluorescence. So here we are.
Thank you, Renaud. So here are summarized the key features of the dual FL. The simultaneous UV-Vis absorbance and fluorescence IMS capabilities give speed and accuracy to your analysis. The system is also corrected with NIST reference for instrumental and sample inner filter effects correction, which means that your analysis is qualitatively good and traceable. The software is fully automated for continuous collection, correction, and quantitative multivariate analysis. Make it easy to use with all necessary tools already implemented in the software. And the system Dual FL is also suitable for auto sampling, flow sampling, multi-position sample changes, and remote operation, making it versatile and suitable for all type of application. Let's really insist now on the major advantage of the dual FL. The system is able to generate EMs in seconds and with a full correction of artifact links to the instrument and to the sample. The embedded absorbance capability gives the real picture of the fluorescence behavior of your samples. The analysis is very fast, within seconds or minutes. EMS will measure all absorbance and emission of fluorescent components. Absorbance, in the meantime, will measure all species independently of their fluorescent properties. Then, this absorbance data provides correction for EMS. Let's illustrate now some applications of the dual FL. The example shown here is related to water analysis. The data have been acquired with the Aqualog version, dedicated to water analysis. These graphs show the fluorescence and absorbance of water samples before and after coagulation and filtration treatments during drinking water processing. When looking for absorbance before and after treatment, one can see that the water has been purified from absorbing species. These absorbance data are also used to correct the fluorescence data. Before and after treatment, one can also notice that the fluorescence behavior has drastically changed. The fluorescence pattern is different, which indicates which type of species has been efficiently removed. The amount of data obtained simultaneously help to have the full picture about the quality of the treatment. Both absorbance and fluorescence measurements can be used to comply with existing regulation in the field of water analysis. Other application for this type of sample could be the study of disinfection byproducts for drinking water processing, reverse osmosis and microfiltration membrane fouling, contamination for pharmaceutical or semiconductor industry, or even effluent for oil and grease contamination in refineries. Other application can be related to oil and polyaromatic hydrocarbons analysis to determine the composition of mixture or to check the quality of final products, for instance, the absence of contaminants or the non-enforcement of petroleum fuel specifications. In material science, quantum dots analysis can also be carried out. As described already, application fields of fluorescence are numerous, and so are the applications of dual FL. In food analysis, for example, it would provide a complete 3D product fingerprinting and brings a large amount of information compared to traditional synchronous scan. The type of the samples which can be addressed is wide: wine, bread, milk, edible oils, beer. All those products have been already successfully tested with the dual FL. In chemistry, the possibility to access the full spectrum within seconds or less would enable to follow kinetics with high speed. It would also prevent delicate samples from photobleaching. Thanks to its optical geometry, with a double subtractive monochromator at the excitation side, the dual FL features a low level of sterlite, making it ideal to analyze diffusing samples, such as powders. Again, the 3D data collection will give information about material structure, mixtures, or contaminants in a very fast and convenient way for material science application. In life science, dual FL advantages are also desirable. The speed of analysis preserves sensitive samples, when the absorbance and EMS data provide certified and high-quality results. And finally, in the field of forensics and counterfeiting, the dual FL would also give a complete fingerprinting of the products, enabling to assess the product nature rapidly and with several points of comparison with reference data. Now, let's get back to the lab to have a live demonstration of dual FL capabilities with Renald.
So thank you again, Romain. Welcome back to the application lab. So what we would like to show you now is really a demo, a live demo of the instruments, and what we are going to record and what I would like to show you right now is a measurement. So of course, I've made some setup. I won't go into detail right now. The sample is in, and just to show you again the advantage of the CCD, the speed of acquisition. So here we are, I just start the measurement, and I will pause all this for some time just to explain you the, what is happening. So keep in mind that what we are recording right now is an excitation emission matrix. So what I'm going to do is just to stop it, just for a while, just to explain you. So here we have the emission range, okay? Here is the excitation, and what we are doing right now is we are step by step changing the excitation, and at each excitation for 0.1 second in that case, we are just recording the full range of the emission. So again, this is the advantage of the CCD. We will get in one shot all the range, okay? So I'm just going to restart the measurement, and if you compare this to PMT, a PMT will do one excitation, 1 point, then the second, then the third, and so on and so forth. Here it's one excitation and the full range of emission. So just to go in a little bit into the detail, right here is the sample with rhodamine, so you get the peak here. I will show you again right now with this, this slide. So of course it takes some time to calculate, because again we get one spectrum, a full spectrum, so at least 1,000 points information in one shot for each excitation. So you can imagine that the number of data is relatively high. So that's why the computer needs sometimes to display the results. So here we are. I'm just going into detail to explain you. So it's a specific sample, a solid sample right now, with rhodamine inside and some other compounds. So typically IMS, and I guess most of you know about this. So again, an excitation emission matrix can give you a lot of information about the sample. So if you know what is inside, you will find out exactly the concentration, for example, with the level of intensity. But then, if you don't know the sample, you can analyze this with typically a parafac, a multivariate analysis, like parafac or PCA, to know what is what, okay? So what I would like to show you now is, again, the advantage of the CCD is we can even go faster than what we have done. So of course, I've made a pause during the measurement, so you won't see exactly the difference. But what I'm going to do is I'm just going to decrease the speed of measurements, okay? So this time each spectrum, each record won't take 0.1 second, but 0.01 second, okay? So we will be a little bit faster. And because of this, I need to modify some information for the CCD, which is the gain in that case, to recover a little bit the lack of signal that I'm going to get in terms of speed, to record enough photon at the end. So just to show you a measurement again, so it's the same sample with a higher speed, and you see that we can still see the sample. Of course, it's a little bit more noisier, it's linked to the timing, but here we are, we get the information and relatively fast. Okay? So again, this is adapted to any type of sample, so this is the advantage of our background in terms of spectroscopy. We are now familiar with different type of samples, so I'm going to show you just again the contour plots. Okay, so we get something which is just a little bit less intense somehow, but actually if I play a little bit with the scale, you will see that we can recover the information. Okay. So this is something which is automatic, and we can, of course, get this easier to use for you. But it's just to show you a little bit how to deal with the software. So we recover the data. Again, it's a little bit noisier, but we get the data, and again, it was very fast compared even to the first measurement. And again, it's definitely faster than what we can get with the PMT. Okay, so just to finish and to show you, here is the sample we get. Okay, so it's typically a polymer with some dyes inside, with a standard liquid holder, what we call the liquid holder. Okay, so it's for cuvettes. So the type of application you can make with this is almost any measurements that you want. Cuvette, standard cuvette with liquid inside. This is water. So typically this kind of instrument, and a little bit more especially the aqualog, these type of instruments are really well adapted to do water analysis. So when we discuss about water analysis, it could be lake analysis, lake water analysis, or rain or tap water. You can detect if there is some compounds inside, so some drugs, some fluorescent compound that you can see. Typically also for the water treatment, you can have before and after the plants, see if there is any evolution and if you remove the unwanted molecules. Okay? So with this holder you can have liquid again, but due to the to our history in spectroscopy, you can also work with solid sample holder like this one with a specific angle. Okay, and with this you can work with any type of sample. It can be a cuvette as well, or something with a liquid inside. You can have wood, of course, or any types. It can be a piece of paper. It can be I don't know, actually, it could be anything. So you can have a piece of wood like this and place it inside and make the measurement. Or it could be some euros from my boss. Okay, so here we are. So you can make measurement on the notes, the banknote itself. Okay, so here we are. These instruments allow you a lot of different type of measurements. It's again linked to our history, but really the advantage right now is the speed of measurements. You will get faster, in the fastest way, you will get more information. So here we are. Hopefully you enjoyed the demo. It was quick, but do not hesitate to come to us, and we will be pleased to help you and to give you information about this. Thank you.
Thank you, Reynald, for the demo. Well, as a conclusion, let's summarize the key advantages of dual FL and CCD detection. CCD effectively brings your spectrofluorometer into the third dimension. By providing fluorescence and absorbance data, the dual FL enables to access both values, which are essential to characterize your samples and comply with regulations. In addition, absorbance helps correcting inner filter effects arising from the sample composition. The possibility to collect IMs in a fast way makes the dual FL the fastest spectrofluorometer in the world. The ease of use of the system is enhanced thanks to available softwares for data treatment, which are able to extract the useful information from a large amount of data. The sensitivity and the possibility of pixels binning enables to work with every type of samples, from very low to very high concentration of fluorescent spaces. All this is available for your applications in chemistry, environment, or material science fields. And in any case, please feel free to contact us and request more information or even testing of your sample. We would also like to remind you that the dual FL is one of our key products from our portfolio. But, of course, HORIBA Scientific's expertise in fluorescence is available within all our systems, would it be for steady state, lifetime, or hybrid systems. Our mission are really to provide high-performance instrumentation for scientific community, to make the researchers and the laboratories benefit from our long experience in designing and production of instruments, and to integrate new technologies and innovative accessories to make our systems the most versatile as possible. Now, I would like to thank you all for your attention, and we are now ready to answer your question.
Just a few words. If you have experienced lags during the broadcast, please know that the webinar is registered and will be available and posted on internet. We will let you know that by email, I think. So, first question, maybe to Reynald. What are the accessories available with a dual FL?
Well, it's almost the same as the other instruments from our company. I mean, all the fluorescence instruments. So there will be some, as I mentioned in the video, some solid sample possibilities. But probably what will be the most interesting with this instrument is the temperature control. So it could be with the Peltier, so with the Peltier effect, or you can have a bath and a cooling or warming bath. So it will be It will be the main possibilities. Then you can have a quantum yield accessory, for example. Almost any accessories which is again available with the standard Fluorolog or the Fluoromax are available with either the dual FL or the Aqualog.
Maybe I will complement with some regarding some other question just arriving regarding the other type of accessories. But of course, we have the possibility to have auto sampler type of device to couple with Aqualog and dual FL, and also fiber optics probe which can be connected through a special platform to be able to analyze in situ, for instance. These are some, let's say, as Renan said, some classical options we can provide with all the type of system we deliver.
So here the fiber optics and in situ probes are available with dual FL. Can you confirm?
Yes, right. They are available. We have this small platform, fiber optic bundle, to be coupled to a probe which can have several designs, but the most basic one is just a fiber connection, a lens, and a housing are all around to be dipped into liquid or anywhere you would need, for sure.
So another question: can I acquire IMS with a monochannel detector?
You go, I go. Well, yes, of course you can. The main difference will be the speed. So with the CCD, definitely it will be faster. So you will acquire with a higher speed, let's say. The disadvantage of the PMT or the mono-channel detector in that case is really that it's going to take time, because you have to acquire for one excitation the emission, and then you move the emission, and then again for the whole spectrum you want to make, and the whole IMS. And really the idea is mono-channel will be longer. And if you think about something which is photosensitive, for example, so if the sample will lose its properties because of the light coming onto it, you will lose some signal and you will degrade or modify the IM you want to record. So for something which is typically photosensitive, so with photo bleaching, and you want to acquire the wavelength where the emission along different excitation, the CCD will be the best tool to use.
Thank you. Another question. I am a Fluorolog 3 user. Is CCD detector available on my system?
So yes, yes it is. So Fluorolog is, let's say, one of the most sold system we have in our portfolio, and it is based on scanning emission and scanning excitation monochromators. But of course, if you have a CCD detector on the emission side, for one position of the grating, you can acquire the full spectrum in one shot as well. So this is available. This type of design, we also made it, for instance, for a specific version of the Fluorolog, which is the nanolog for carbon nanotube analysis. And then the detection is not purely with CCD, it's with an infrared array detector. The purpose is the same, is to acquire a full spectrum in one shot. So this is let's say, the most common configuration where we have array detectors onto a Fluorolog 3. But for sure, CCD detectors by themselves for the visible range, they are available on the Fluorolog 3 as well, to be able to do also some fast IMS in this case.
Thank you. What is the difference between CCD and array detection?
So, yeah, a little bit related to the previous question, but for sure, CCD. So it's really a two-dimensional detector. So you have pixels in two directions. For the array detection, in fact, it's more or less the sensitive components which are stacked together in one direction, but still it enables, if it's really in the direction of the spectrum, you can still acquire one spectrum in the full shot in one shot, yes.
What are the difference with an Aqualog? Big question.
Almost none. For the dual FL, for the moment, the dual FL is almost the same thing as the Aqualog. Again, we were discussing about the accessories, so the accessories are similar. Yeah, there is almost no difference. There will be probably more development on the dual FL in the future, but we are just still thinking about it. So.
From the purely hardware point of view, yes. And then for the Aqualog, what we still provide, in addition, is more the method and the software package to be able to really dedicate the system for one given application. So everything related to data treatment and to extract the information purely dedicated for water analysis and CDOM analysis. This is mostly the main difference from the software point of view, I would say.
Okay, so it was one question. Someone asked if it was possible to do the same analysis with dual FL and with Aqualog.
Yes, it is. Yes, from the purely hardware point of view, there will be the same kind of specification and so on. The design is optical design is the same.
Okay, another question. What about factor correction with multi-channel detectors?
Yeah, we need some precision on this question somehow, maybe. For typically for the dual FL, the grating is fixed, so we have the full correction. So on the Aqualog and the dual FL, the correction is fully introduced into the system at the manufacturing. For the Fluorolog, for example, if we go for the Fluorolog, there will be a little bit more work to make on this according to the position of the grating and how you want to use the grating. But here we are. It's definitely doable, and most of the time introduced into the machine at the manufacturing.
Yeah, for the Fluorolog, for instance, the correction more generally is required for given position of the grating, which means that you can correct over the full range, but for given central wavelengths. So this is doable. It's easier to do on fixed grating that we have in dual FL and Aqualog, but yes, you can do both.
Another question, how are Raman and relay dealt with during analysis?
So for the analysis, it will be so we have two level of analysis. So I would say the analysis within our software will be we can mask actually the relay and the Raman. So we have some tools to calculate what are the position. Well, for the relay, it's quite simple. It's exactly at the same wavelength as the excitation. For the Raman, we know where they will appear, so we can remove them if we want. So it will be done with our software this way. And then it's up to you actually. You can then remove them another way with the software you are using for the analysis. So typically, if you are working under MATLAB, you can have your own macro and remove the signal you want, or to I don't know. We know already some customers who are totally removing the signal, but some of them are just smoothing to keep the flow of the level somehow of signal between the 2 points the point around this Raman or this relay effect. It's really up to you. We can give you some tools to start with, and then it's really your choice to know exactly what you want to do with the analysis.
Thank you. Okay, so many questions today. Another one. Can I carry out lifetime measurement with a CCD?
Unfortunately, no. For those who know me, they know that I love lifetime, so I will say it's a pity. No, you cannot with the CCD. The CCD is not responding fast enough. The response is not fast enough to get a real-time result measurement. There are some possibilities probably in the future with the gated CCD, but for the moment it's not what we want to use. If you are interested, just let us know. It will be interesting for us to know if it's something that you find in which you find some interest, for sure.
And what is the sensitivity of CCD compared to PMT?
So CCD sensitivity, we are as you saw, maybe it's limited to 16 bits, meaning that the pixel well depth is limited, of course, for the collection of light. But what we can do to increase the sensitivity of the CCD is dealing with binning the pixels altogether. It means that if in some pixels you have no electrons falling, and in some others you can sum all together the pixels which corresponds to the same wavelengths all across the CCD in vertical direction, and then gaining more signal compared to analyzing just one single pixel, which means that in the end the sensitivity of the CCD in this case is very, compares very well to the PMT. And for instance, the specification we are giving for the dual FL for the sensitivity is 20,000 to 1 signal to noise ratio for the Rotter Raman peak, which is a standard way to measure the sensitivity of a detector. So I would say it compares very well, and maybe even better in some cases for some samples. Yes.
Another one, do you have a CCD with wavelengths up to 620 nanometers, which is possible with Aqualog?
So we have it. We still have this possibility to adapt this type of detectors. Nevertheless, we think, and so it's no problem, but we think that for addressing the most diverse application as possible, the possibility to go up to 800 nanometers is really an interesting parameter. So that's why we prefer to say we have this type of two configurations, from 200 to 800 and from 250 to 800. Of course, we have also available some CCDs stopping at 620, which are possible to adapt, making that we have then version between 200 and 620 and 250 up to 620. The spectral range is more limited, so for some application, and especially in water analysis, it has been demonstrated that it could be enough, but having the possibility to go further in the red seems interesting, so that's why we push these two versions.
Yeah, for sure. I will complement that. Yeah, the larger wavelengths you can get, better it will be, for sure.
Another question, what is the range of emission for Fluorescence 3? And is it just up to 600 nanometers as shown in the real measurement? Let's start.
Yeah, it will depend on the CCD that we will add, actually, with this idea of multiple wavelength record at the same time. As Romain was mentioning earlier, we can go with an in-gas array, and well, the 600 will be higher than this. You can go to 800, and you can go above this. With the Fluorolog, it's a little bit more like a tunable, I will say, tunable instrument. So it's really according to what you want to do. We will have most probably a positive reply to give. So I would say we can go higher than this. We can go 600, but you can go definitely higher with the Fluorolog.
Yeah, and just to be sure that there is no confusion, the system which has been demonstrated during the live demo was the dual FL. So dual FL, here was the version which is the limited up to 620, so as shown in the real measurement, as mentioned in the question. For the Fluorolog, this is really the modular system, the very flexible system, which can go, yes, really far in the infrared. Then you need to adapt the detectors. And of course, one of the versions of the Fluorolog 3 is the nanolog version, which is dedicated to carbon nanotube analysis. And for this, you have a red detector, which is able to go in the infrared, and then making possible to analyze IMS in the infrared for carbon nanotube. So dual FL is a compact system based on CCD for what has been demonstrated during the live demo. Fluorolog 3 is really a modular system, which is bigger, let's say more versatile in terms of capability in the infrared, and which can be used with array and CCD detectors as well.
So another one, is the outlier detection possible during analysis, or does this have to be done in post-processing?
Detection possible. I don't understand really the question, quite frankly.
It means that if there's, maybe we could precise the question, but
yeah,
if outliers means one sample among the others, which is an outlier, then most probably it will be done afterwards during the chemometrics treatment, because it will appear as really different from the others. If you mean outliers by kind of very special behavior in the spectrum with much more intensity or something very strange in terms of fluorescence, then it will most probably as well be done afterwards in the post-processing, because during the measurement you acquire just IMS, and then you can apply during the measurement or just after the treatment for data correction, but they will most probably consist in relay filtering and blank masking and so on, which are not really directly linked to the sample you're analyzing, but really for the performance of the instrument, correcting the instrumental factors. So most probably I would say generally after post-processing. But it really depends if you are doing your model live or if you are really post-processing the data 2 days after. It makes a difference for sure.
Well, we can complement because the idea if you are thinking about a blank can be measured in advance somehow before your real measurement, the sample measurement, and the system will automatically remove it. If you ask it to do it, it will remove it. So but most of the time it will be most post-acquisition data treatment, yes.
Question of price now. In terms of price, which is the difference between dual FL and Aqualog?
So, pricing question is always a bit challenging to answer because, as we said, it depends on the configuration and the type of options. So this is a commercial response. But of course, from the comparison between the two, Aqualog and Dual FL, they are very close in price because, as we said, the instrumental design and the optical path, they are very similar. The main difference, I would say, is if you buy an Aqualog with a full package for data treatment, if you do not develop by yourself your own methods, then you will have to add the price of software routines and software methods to be able to run an Aqualog. But in this case, I would say the difference in price would be within the range of 5 to 10% in favor to the Dual FL if you buy the Aqualog with the software.
What is the dynamic range and what about the stray light?
The stray light, well, you will have some for sure, and the idea will be that you will saturate. This is the idea with the CCD. With the PMT, so with the mono-channel detector, you will have an effect of saturating the signal. So it will grow, and then you will start to gently but surely decrease the capability of the PMT to record the incoming photons. With the CCD, you will have a clear cut after 65,000 counts. So you really have something which grows and then stop, and then the decrease of the fluorescence if you have a standard sample. So area for the stray light, it will be really on off. But most of the time you remove it from the sample, so we don't care about it somehow. And keep in mind that it's not the same as the mono-channel detector. If you go through the stray light with the PMT, after this stray light, the PMT will need some time to recover. So a part of the signal will not be well recorded. With the CCD, keep in mind that they are like separated detectors, close one to the other. So even if you saturate some of them, the one next is not saturated at all. So it will measure normally the signal. And then the other part, so the dynamic range, I would say as an application guy that the PMT has a little bit better range, dynamic range. The CCD is linear up to this saturation, but in terms of count, the PMT can go a little bit higher with the linear behavior. So
there was a slide in the presentation mentioning this as well. For sure, as Reynal mentioned, the pixels, they are spatially separated. When you have a PMT, you have just one sensitive surface to detect all the photons. So of course, all the photons will go and contribute to saturate the same sensitive area. When you are on CCDs, other pixels are separated. You split, I would say, you share the photons on all the pixels which correspond to the same wavelengths, which means that in the end, if you have enough pixels in terms of vertical direction, and if you share your light on all the pixels, you can see that the linearity of the CCD can be, by summing all the pixels, quite nice. For sure, the linearity and the dynamic range, let's say, of one pixel versus one PMT, it will be much lower. But if you sum all the pixels together, you can reach the dynamic range up to the 10 to the power 7 or 8, depending on what you have in terms of pixels, as mentioned in the slide you have.
Okay, so it seems it's the last question now. Can a fluorolog do absorbance and fluorescence measurement?
Thank you. Yes, it can. For sure, fluorolog, so it's made for fluorescence measurement, but of course we have also specific options which are absorbance and transmission measurements. which come on the front face of the Fluorolog, and which enables to measure the absorbance and the transmission of given samples. So of course you can use this tool as a standalone tool, let's say, to measure really the absorbance of the system, of the sample. But you can also use, as we mentioned, the data generated by this absorbance device to be able to correct, for instance, your spectrum in fluorescence.
Thank you.
And this is also available on the Fluoromax. Actually, we are talking about the Fluorolog, but the Fluoromax will have the same behavior. You can add the same absorption accessory with the Fluoromax as well. It's a good tool to implement a system.
Okay, so 2 more questions. Sorry, guys.
No problem.
With Aqualog, we often have a problem of saturation. Is it possible to get a fluorescence up to
50,000 counts.
50,000 counts.
With CCD?
Yes, we can. Actually, it's higher than this. And yeah, again, I would be interesting to discuss a little bit about this question, but it's not really a problem of saturation. You can have saturation for sure. It will not be a problem. You can modify a little bit the way of doing the measurement and get rid of this. Most of the time saturation will appear on the stray light. So this is something that you are not using in fluorescence. So I would not say that it's really a problem. Probably we, if we can, we have to discuss a little bit more about this for sure.
Okay, so let me see another one. Sorry. What is the detection limit for fluorescence, for example, with the Fluorolog compared to the dual FL?
Well, I will answer quite easily. I've never tried. We have no information about this, but I would say that it's something that we need to do. It would be the best answer to give you. I don't want to go into numbers. I don't know. It's something that will be interesting to try. I don't know. Maybe on the brochure we have some information, but I don't know about this.
For the Fluorolog by itself, it's really a system which is high-end and a very high-performance system. So if you are chasing for a limit of detection, very low concentration, having a Fluorolog with a double mono in excitation, double mono in emission will help reducing all the stray light, all the background, and to have a very to be able to detect very low signals, so very low concentration. Dual FL is mostly a system which is dedicated, let's say, for analytical purposes. There is less, I would say, flexibility in terms of the range of options, but it's very quick. So it means that for a huge number of samples, if you want to analyze quite fast, this would be the instrument of choice. In terms of limit of detection, it will not be, I would say it will not be so bad. I don't know exactly what would be the limit, but for sure you have a double subtractive in excitation, so good stray light rejection in excitation. In emission, you just have one fixed one stage mono, so most probably the performance will be a little bit less.
Yeah, probably a little bit less, but quite comparable. I would say for sure the dual FL is working very well on this level as well.
So last question. When measuring samples with a really low fluorescence signal, is there a way the signal can be enhanced using a Fluorolog 4 instrument?
So I will do the joke, you make it or I do it. In the question is Fluorolog 4, so I would say, oh yes, a new model. But I'm just joking about this, no worries. Yeah, there's always a way to enhance the signal. I will recommend to either to do some accumulation or to increase the integration time. It will be the best thing, especially if you need to keep resolution. The 2 parameters that can be modified or to emphasize, let's say, I will say, it's for sure the integration time, and then accumulation. The accumulation with the average type of accumulation will be really, really useful to emphasize the signal, which is very low, and to make difference between signal and noise.
Okay, thank you, Renald. Thank you, Romain. I think that the webinar is finished now. Thank you, everyone, for your questions. And so it's time to say you bye-bye.
Thank you.
Bye for now.
Bye.
Bye.